Good morning, one and all. Welcome back to the video lecture series, Linear Integrated Circuits and its Applications. This is Dr. P. SREENIVASULU. Today, we are going to discuss about DC characteristics of op-amp. Now, you see, whatever we are analyzing the op-amp for theoretical case, we are assuming this op-amp is an ideal op-amp. See, the ideal op-amp, it draws no current from the source and it is also independent of temperature. But when we are coming for op-amp, the internal circuitry is a transistor. So this transistor always takes some current and it is also responds differently for current and voltages. And it is also depends upon temperature because the transistor parameters, beta, leakage current, VB, these are all depends upon the temperature. So the real op-amp is differently act as an ideal op-amp. But the characteristics of ideal op-amp, we are going to be reached as well as we need to try to reach that goals. That is the difference between ideal op-amp and practical op-amp. Now coming for here in the DC characteristics, we need to see four parameters we are going to be testing. One is input bias current, another one is input offset current, next one is input offset voltage, next one is thermal drift. So these four parameters we are going to compare with your ideal ideal op-amp with the real op-amp. So suppose input bias current, what is the ideal value and what is the practically rough value we are going to get with the real op-amp. Now you see this input bias current circuit diagram if you observe here. So consider this op-amp. There is a IB plus and IB minus. What is the meaning of IB plus, IB minus? The current drawn by, the base current drawn by internal transistor at non-inverting terminal and the current drawn by inverting terminal of base internal. It is a IB minus. Generally, if you see an ideal op-amp, in the ideal op-amp, this IB plus and IB minus both are 0. We are coming for this practical op-amp. If you observe here, we are connecting a simple inverting amplifier circuit. In this inverting amplifier, if I make VI is equal to 0, if I make VI is equal to 0, generally whenever VI is equal to 0 and already the non-inverting terminal is connected to grounded, at the inverting terminal also the voltage is need to be based on the concept of virtual ground. We are going to be assume it is also 0. So input is 0, other potential at inverting terminal is the potential is 0. Usually there is no any current. That is I1 is equal to 0. And from the concept of ideal op-amp, either of the input terminals draws no current. But it is not happening in practical op-amp. In practical op-amp, there must be always some current drawn by either of the input terminals, that is non-inverting terminal as well as input terminal. So that is current, that current we are going to be called input bias current. Input bias current. Already there is the device is properly biased. So that's why whenever even if you not apply voltage, there must be some initial current through these terminals, that is internally there is transistors. So that input bias current we are going to be measure here, the average of non-inverting base current, inverting base current. So if you see here, IB plus IB minus by 2, IB plus IB minus by 2. So it is the actual input bias current in real op-amp. Well, coming for this 741 IC, standard 741 IC, we are going to see in the laboratory also for analyzing this op-amp. So, a 741 IC, it is a bipolar op-amp. Usually, the op-amp is going to be designed both the transistor and FET version. Now, here we are assuming this one, this 741 IC with bipolar bit with the transistor. The input bias current is 500 nanoamperes or less. 500 nanoamperes or less. We see here, it is a 500 nanoamperes means, usually it is a very less current, but even though it is very less current, it is not fulfilled with our ideal op-amp case. We are designed the circuit diagram, we are assuming that, we are analyzing that either of the input terminals draws no current. But here there must be some on an average of these two currents if we observe whatever the current drawn by first transistor, that means at non-input terminal, and whatever the current drawn by the current another terminal, that is another transistor, there may be some current is there. If suppose if you replace this 741 IC with instead of considering this bipolar, if you go with a FET version, now if you see here, it is still very less. 50 picoamperes, around 50 picoamperes. 50 pico means nano 10 power minus 9, pico 10 power minus 12. So very, very, very less amount of current is drawn by these FET terminals. But anyway, it is not going to be get zero, but approximately it is very less value. Now, this problem, how can you overcome this problem? So, consider a basic inverting amplifier. We know, all of you know inverting amplifier. The input voltage VI is set to 0 volts. The output voltage V0 should also be 0 volt. So, that is our aim. Whenever we are designing an inverting amplifier, whenever we are designing an inverting amplifier, whenever input is 0, we are expecting the output is 0, but that is not getting here because there is some current is drawn by the terminals, inverting terminal or non-inverting terminal. So we find that what is the output voltage? That is the offset voltage, means it is unwanted voltage. Offset means we don't want this voltage. Whenever input is 0, based on the concept of operational amplifier, it is simply inverting amplifier means output is entirely depends upon input voltage. Input is 0, output is, we are expecting output is also 0, but we are not getting output is 0. You see here V0 is equal to IV minus into RF because already there is no any current because VI is 0, but the current drawn by this base terminal of transistor, there is some small amount of current. So that V0 is now depends upon this whatever the current drawn by the inverting terminal. So V0 is equal to IV minus into RF. Suppose usually RF if we connect 1 mega ohm feedback resistor. Now already IB minus we are assuming that on an average 500 nanoamperes. 500 nanoamperes into 1 mega or 10 power 3 into 10 power minus 9, it is around 500 millivolts. So this much of offset voltage is not at all acceptable. So that is the problem with the op-amp. So the output is driven to 500 millivolts with zero input. That is you see here. We are applying any input, we are not applying any input signal, but output there is present at 500 millivolts. So it is because of input bias currents. In applications where signal levels are measured in millivolts, suppose we are using this op-amp in different applications, different field of applications, there is many variety of applications are there. Suppose we are in some particular applications, we are going to be use this op-amp in the output is also in the order of millivolts. So it is entirely gives the false result. So that's why it is the problem with whatever the current drawn by the op-amp. So you need to address this one. You need to overcome this one. You need to eliminate this one. That is our main motto. So that's why this offset can be compensated as shown in figure. It is going to be compensated where the compensation resistor has been added between non-inverting input terminal and ground. So whatever the problem we are getting, this problem is going to be compensated if we connect a non-inverting in between non-inverting terminal and ground, one compensation resistor or compensation. So IB plus flowing to the compensation resistor or compensation, develop a voltage V1 across that. So if you apply the KVL there, you apply KVL here, you see here, it is, we are connecting a, previously this compensation resistor is not there. Previously, this compensation resistor is not there. Now we are connecting this compensation resistor. Now if you see, if you analyze this one, output V0 is equal to I2 into RF plus the voltage difference between these two is 0 plus whatever the current is flowing IB plus. So you consider that current also. So that's why you write this formula, minus V1 plus 0 plus V2 minus V0 is equal to 0. So what is the minus V1 here? You see, voltage developed across this particular R compensation, and that voltage difference between these two, we are applying KVL here. So this voltage plus this voltage plus this voltage plus output voltage. So finally, V0 is equal to V2 minus V1. So V0 is equal to V2 minus V1. Now you know what is the V1 from this? What is the V1 current flowing to this? What is the current flowing? IB plus. So IB plus into R compensation. So finally, IB plus is equal to V1 by R compensation. So what is the I1? V1 by R1. So you see, what is the I1? I1 is equal to V1 by R1. I1 is equal to V1 by R1. So I2 is equal to V2 by RF. Now, for compensation, V0 should be 0. Our aim is, what is our aim? We are getting some offset voltage. So we need to compensate. We need to make this output voltage is 0. So V0 should be 0 for VA is 0. So that from that equation, I2 is equal to V1 by RF. I2 is equal to V1 by RF. Okay. Now, if you write KCL at node A, IB minus is equal to IB2 plus IB1. You see here, this one, here, whatever the current, it is I1, it is leaving current, it is entering. These two currents are entering, this current is leaving. So, IB minus is equal to I2 plus I1. So, V1 by RF plus V1 by R1. So, V1, these two are parallel, R1 RF by R1 plus RF. Okay. What is the I2? I2 this one. I2 is coming from this one. I1 is this one. It is, this current is non-inverting current. Now finally, it is going to be get V1 V1 into R1 plus RF by R1 RF. Okay. It is generally it is R1 plus RF by R1. Now assuming whatever the current drawn by two transistors almost same. So IB plus is equal to IB minus. IB plus is equal to V1 by R compensation. So V1 gets cancelled. So R compensation is equal to R1 RF by, finally R compensation is equal to R1 RF by R1 plus RF. It is nothing but parallel combination. So we need to select the compensation resistor in between non-inverting terminal and ground. So whatever we are connecting, a feedback resistor and R1 resistor, you take a parallel combination, and then whatever the value, that value is going to be connected. Then if you observe the output voltage is compensated. So there is a no offset voltage. So finally conclusion is, this compensates the bias current that corresponding to R compensation should be equal to parallel combination of resistors tied to the non-inverting terminal, non-inverting inverter to ground. Okay. I'm stopping this class. We'll see you in the next class.